Okay, so today we're going to finish up your Pennium lab from the other day. If you were not here in class, you can go on and use the data that I have for my pennies. I can organize my data where I had my four pre together and then my 16 posts together. It didn't really matter. So if you were not here, if you could go on and fill in your masses and years for the masses that I have. My total mass of all of my pennies came out to be 52.33 grams. Hopefully, I added those all up correctly. Um, let's take a look at our calculations for our lab. If you could follow along, make sure you have a calculator. You're definitely going to need a calculator and have your lab open so you can fill in the answers as we're going along. So the first calculation says to inspect your data carefully. Determine the number of isotopes of your pennium that are present. So let's go back and take a look at our different masses. Now, I know that we said isotopes are going to have different overall masses, but remember, pennies are not perfect. Okay, so some students could count this up and be like, well, I got 10 different isotopes in here because I have 10 different masses of my pennies. Remember, pennies are man made, they've been through circulation, so they're worn down, they have gouges, they have scratches, so they are not going to be perfect like atoms would be. But if we look at the data overall, we're going to see that we have two very distinct different masses here. So we have one mass or one isotope that has the mass of about 3.1. And then we have another mass that is about 2.5 ish, okay, or 2.49 ish. So we can see that we have two distinct different masses. So we're going to say that there are two different isotopes of pennium because we see the two distinct different groups. And we're going to give them names. I'm going to call the one group pre 1982 and the other post 1982. Calculation number 2 wants you to calculate the fractional abundance of each isotope that you have in your sample. So this is the formula that you have to determine your fractional, or I like to use percent abundance of your pennies. So you need to look at overall. We have two different isotopes. We have our post, and we're going to have our pre. Okay, so how many post pennies did we have in our sample? Well, we had 16. How many atoms or pennies did we have total? We had 20. So 16 divided by 20 gives us 0.8, or we could say 80%. So yeah, that makes sense. Most of the pennies that we come around in contact with are going to be newer pennies. Pre, well, we had 4 pre out of 20 total. So that's going to be 20% or 0.2. So this is your fractional or percent abundance, 80 and 20. 80% for post, 20% for pre. Okay, so calculation number 3 wanted you to calculate the average atomic mass for each of your isotope. So to do that, to find your average atomic mass, you're going to add together the total mass of your pennies for each isotope divided by your total number of pennies that you have for each isotope. So you may have to pause this video. So for instance, we have our post and we have our pre. Okay, so I know I had, so I'm just going to start going right on down my list here. Via will let me go back. So my first pre, I have 2.5, I have 2.50, I have 2.48. So I'm going to start adding all of my posts up together. Okay. So once I have added all of them together, I am going to divide by 16. Okay. And that, when I added them all together and divided by 16, I just found the regular average. That came out to be 2.498. Let's go on and round your average mass for each of your isotopes and have two decimal places. So let's go 2.50 is what we're going to go with here. Okay. We're going to do the same thing for our pre. The pre should not take quite as long because you just have 4 pennies there in the pre. So I think I had 3.1, 3.08, 3.2, 3.09s. Okay, so you're going to add all of your pre's together and you're going to divide by 4 because there's only 4 of them. So when I did that, I ended up having the mass of 3.09. So that's going to be my mass of my pre. So my post mass is going to be 2.50. My pre's mass is going to be 3.09. And I'm going to use these two numbers in my next calculation. Okay, so calculation number 4 says using the fractional abundance or percent abundance and the average atomic mass of each isotope, calculate the atomic mass of Pennium. So here is the equation or formula that I made for you to determine or calculate your atomic mass or your weighted average. So we're going to use our answers from calculation 2 and calculation number 3. So for our post, we said that the percent abundance was 80. So we're going to just change that to a decimal, or leave it in the decimal from our calculation. And we're going to take that times the mass that we determined our posts to be. The average mass of our post we determined was 2.50. And I want you to use your numbers, not mine. So everybody will use 0.8, but I want you to use your mass from number 3. The next one is going to be our pre. So we calculated the percent to be 20%. So that would be 0.20 from calculation number 2. So everybody will use the 0.2. And then I want you to use the mass that you determined from number 3 for your pre to be, in which mine was 3.09. I'm going to multiply the 0.8 times 2.50, and that's 2. If you want to use your calculator and enter this all at once, you can, but just watch for parentheses so your calculator does not take over order of operations. Then 2 times 3.09 gives me 0.618. Then I'm going to add those together, and that is going to be my mass of this new element that we discovered of Pennium. My mass was 2.618 AMU for Pennium. Or if we just want to focus on one decimal place, that may get us all having the same mass of 2.6. Okay, so let's start our question. So we have the critical thinking where we're going to analyze and draw some conclusions from looking at our data. The first question says, was the mass of 20 pennies equal to 20 times the mass of one penny? And to explain. Well, if you look back at your overall data, no, you're not going to be able to just find the mass of one penny and then take that times 20 because of the fact that your pennies are going to vary from each other. And you had two different masses. You had the mass of 3 and you had the one with the mass of 2.5. So that's why that will not work. In question number 2, in what year or years did the pennium of mass change and how could you tell? Well, hopefully you figured that out that it was in 1982 because of in the pre-lab I mentioned that we had pulled or tried to pull all the pennies with the date of 1982 because some weighed more, some weighed less. So they actually minted both types of pennies. That you would notice that some weighed heavier, some were a little bit less weight. Question number 3, how can you explain the fact that there are different isotopes of pennium? Okay, well, pennies in the year 1982 changed materials. Okay, so they were actually made before 1982. They were made with 95% copper. Okay. Um, but it was costing too much to make these copper pennies. They were actually, the pennies were worth more than a penny. So they ended up minting them and using substances or metals that were lighter. So today, or starting in 1982 with our post pennies, it is zinc with a very thin layer of copper. There was one year that pennies were actually minted. 1943 pennies were actually made of pure steel because copper, and this also affected your other coins too, nickel, they were just too valuable to be used. So between 1942 and 1945, your Jefferson nickels, your Mercury dimes, your Washington quarters, and your Walking Liberty half dollars were actually made of fine silver. But in 1943, they actually end up having to make your pennies out of steel instead of copper. So a few years ago, when we were on vacation, I had actually found some steel pennies in a lighthouse exhibit that they had there. So I made sure to take pictures of them to show how World War II had impacted our minting and how I could apply this to our Pennium lab. At the time, my daughters were wondering why I was taking pennies, so hopefully now it's starting to make sense. So let's look at critical thinking application, where we're going to apply this knowledge with what we have been learning in class. So our first question is, why are the atomic masses for most elements not whole numbers? Well, looking at your back at your mathematical calculations, hopefully you've realized that it's a weighted average that we're working with. You don't have parts of protons and neutrons. It's looking at their percent abundance, how often or how that probability the probability that you would encounter one of those isotopes. So that's where the decimals come from in your atomic mass. It is from the weighted atomic average of your isotopes for your elements. Question number 2 says, how are the 3 isotopes of hydrogen alike and how are they different? So for this question, I would like for you to refer back to your notes. This was the day that the videos were not working and you ended up having 2 different videos made. So you want to look back at your notes on hydrogen 1, hydrogen 2, and hydrogen 3. We actually had the names protium, deuterium, and tritium. It's that first slide, first page of notes, and we wrote down how they were similar subatomically. So that's where I would like for you to go back and look and answer number 2 on your own. And I would like for you to answer question number 3 on your own also. Um, Copper has two isotopes, copper 63 and copper 65. So remember the 63 and the 65, that's referring to their mass. The relative abundance of copper 63 is 69.1%, and copper 65 is 30.9%. Calculate the average atomic mass of copper. So, using this formula up here and the information that you're given about the two isotopes of copper, its mass and its percent abundance, if you could calculate its mass or AMU. And then at that point, if you could go on and submit your lab.